In that video, we'll simulate a large language model control Mars rover, and we use Raspberry Pi. In my case, it's Raspberry Pi 4P with 8 GB of RAM. The bigger RAM amount is very important here to run Zephir LLM locally on that. Basically, we will see if we will be able to deploy some relevant AI application for our robot on something such small as Raspberry Pi. Why do we want to do it when it's ChatGPT available everywhere? Well, basically, there's some situation where we have no access to internet, as for example when we on Mars, and in that situation we need to have LLM run locally. Let's try to run our AI brain Mars rover. Let's log into our device through the Dataplicity platform and let's choose our user to Pi. Dataplicity will allow us easy debug of our device and remote access of it. I will not show today how to install it because you can find it in I think every video on that channel. Now let's just proceed to the core of our video. Let's go to Ollama.ai and let's copy download code for the Linux. Execute it on our Raspberry Pi and wait until Ollama will be installed. After we need to download our model on which we will work on. Let's go to the Models tab on Ollama page and let's find Zephir models family. We can just use that command Ollama run Zephir to download base model, but we don't want to use base model but want to use some quantized model. Quantized models are basically much lighter and requires less resources than base model, but not very less intelligent. So drop on the weight and model complication is much bigger than drop on the intelligence of the model. Let's choose one of the quantized model, for example Q4 or Q5. Copy the installation command and let's paste it here. We need to wait for a while until the model will be downloaded. Okay, finally it's here and we can test it how it will perform. Let's take case of our Martian rover and let's start from the role definition. You're Martian rover and your task is to find rare mineral, get samples of it and return to base. Make decision about your future action based on your sensor observation. And now we provided his sensor observations. Basically 4 cameras around him, front camera with dangerous crater, right camera with clear space, left camera, high rocks, and the rear camera also high rocks. After that we are providing position system data, which shows the base at rear left half of kilometer from here, and data of samples container sensor, showing that samples container is empty. We have no mineral yet. Let's see what our model returns. Well, first of all we can see that it's working. It's not very fast. Now you can see natural speed of that model, but after that I will just speed up the video. And we can see that our model discussing first sensor observations. For example, that Martian rover should avoid going forward as there is dangerous crater, but right movement is possible as there is clear field. But after that we can see that model starting to get lost in his own words. First of all, he talking that mineral container is empty and he should prioritize collecting the rare mineral, which is, well, good reasoning. But after he tells that Martian rover should move towards the left to avoid the high rocks, but well, at left side we have high rocks, and then head back to base to deliver the samples which he has no yet. So what do I think about his response? Well, basically a few videos ago you can find video about installation Llama CPP on the same Raspberry Pi, but it was really generating just random noise on its output and nothing else. But now in the case of Zephir we can see that he really providing good reasoning. His words really have sense. Well, still he is getting lost in his reasoning. He's not perfect. But I see here a huge progress on the development of small large language models. So in that case, I propose to make that case simple for him. For example, we can programmatically check if our container is empty or full and based on that decide in which state exploration or mineral gathering or returning to base our rover should be. Let's simplify our prompt. Let's ask him for just one task, the exploration. Let's remove sensor data about container, and let's see how he will perform now. Okay, again, he is describing possible direction of movement. And well, he basically reasoned good about where he can and can't go, but finally he takes bad decision to go left side, again to avoid high rocks where we have that high rocks. Okay, after few more takes, I found a designed much better prompt for which our model provides also much better results. This time task is return to base, and I ask model first to reason about where our rover can and can't go. After that, to make on the basis of reasoning conclusion about each direction and just write you can or can't go that direction. After that, again, I'm asking him about reasoning about where he can go, basically where he should go. And in fourth step, I'm asking him about final decision about where he will go. There's few tricks in that prompt. First of them is dividing his complex task for few small tasks to make it just easier for a model to think about it. And other trick is using the chain of thought method to make model think first before making the decision. Both of the tricks usually provide better results. And let's see what our model have respond. In first step, we can see that he lists all the 4 directions, and for every direction he provides very intelligent reasoning about is it possible or no to go that direction. In second step, he writes his conclusions about it. In third step, we can see his reasoning on his recommendation of movement. And finally, in fourth step, we can see his decision. Martin rover will move towards the left to collect mineral samples and then return home by traveling in the straight line towards the base at the rear left, 500 meters away from its current location. Wow, much better. Okay, for now it's enough tests. Let's go to the practical use case. Prepared a code to control our Mars rover, and let's look at that. It's really interesting. First of all, we have 3 different prompts for 3 different situations. For the exploration, mineral gathering, and return to base. Why? Basically, we want to minimize our prompt length to increase chance of model to not get lost on that informations and instructions prompt has. Basically, the simpler prompt you have, the chance the model will work good is bigger. We'll do next interesting thing. Basically, we'll find state in which our Mars rover currently is, and let's assume we'll do it using our rover sensors. For example, if rover cameras can see any mineral around and the mineral container is empty, we should be in exploration state. If mineral container is empty but cameras can see somewhere the mineral, we in the mineral gathering state. And when our mineral container full, we are in the state return to base. So, basically we're doing that choosing programmatically to maximize chances it will be done good. Basically, one of the main rules of AI development is if you can do something programmatically, do it programmatically. So in that part of code, we can see that independent in which state we are, we choose an appropriate chain for our LLM. What is chain and how it built it, we will talk after a while. So there is 3 prompts for every different states. They are kind of similar. First of all, we get our sensor data provided as variable here. That part will be swapped with the sensor data provided. After that, we have instruction. First of all, we given a role to our LLM. So in the case, your Mars rover. Next, we define a task. You need to explore surface. And after that, we asking it to analyze which direction it should go based on the sensor data provided. It's very interesting because here we're saying take a deep breath and analyze something. If you think about it, it could look a little bit strange. Basically, yes, how does LLM could take a deep breath? But here I'm using so-called latent space activation technique. This theory that tells us that by our keywords we are using, we can activate some parts of our model's brain. So, for example, if we asking it to take a deep breath, it's very probable we'll activate some part that will responsible for more calm and better solutions. When our LM was trained with data in internet, we wanted to be related to more quality data, where responses was not written fast, just in run, but were written with big quality, really slowly, and when author were thinking about what he was written. So here the same. Basically, we asking LLM to think better and provide better response. We asking to return JSON, and here we showing an example of JSON. It's very interesting because we have our instructions here about JSON parameters inside of that example JSON. That way we can use a shorter prompt, provide the better example for LLM to better visualize for it what do we want from it to return. First of all, we asking it to provide step-by-step reasoning about what direction should we choose and why, basically to think first. That, by the way, is a called chain of thought method, which allows model by explicit thinking, well, think better, return better answer, and also for us it allows to debug thoughts of the model. And after reasoning were written, we asking it about final answer. Just choose one direction from front, right, left, or back. One more time asking to return only JSON, because basically sometimes Zephir can return you some not just JSON, but this is JSON and next JSON. And after that we can just get a parse error. Rest of the prompts are similar, but only the task is different. And another interesting thing, you can ask why did I place sensor data before instructions and not after? Well, the reason is LLMs basically pay more attention to data that is provided at the end of the prompt. Also, it paid a lot of attention at the beginning of the prompt, but paid much less attention at the middle of prompt. So that's why our most important informations, instructions that we want for LLM to be understood good, we are providing at the end of our prompt. So let's return to the code. Here we have a getSensorData function that basically will simulate our data from Mars rover. In real life, we will build in such Mars rover that will be more advanced, and for example, for data from our cameras, we need to translate our camera data to text, and for this we can use some image-to-text models. As for example, lastly released GPT-4 Vision, not well, as GPT-4 Vision is available only by API, not locally, we'll use some open source models. For example, you can just go to Hugging Face and find here image to text models. You have a lot of things to choose. So here we just emulating what our camera sees, and just for example for exploration, where we have no mineral at cameras, our camera just sees some rocks, clear space, craters, or again clear space. Here we define also our state, and our function will return sensor data in text and current state. As I said before, based on the state, we'll choose the prompt for our LLM. Here, using Ollama library, we're reading our Zephir LLM, setting temperature to 0 to maximize chance of repeatable responses. Here we're reading our prompts and also using prompt template feature from our langhain library to parse the prompts. And next here we're creating a chain of our prompt and LLM. The appropriate chain is created. We invoke an LLM with data we pasting on our chain. So basically the sensor data we have here going to our prompt here. And after that we activate a move function. In a real robot we need to activate some function of movement, but in our case we just getting direction from direction feature of our JSON, this one, and after that just printing that we move into that chosen direction. That's basically all. Now let's test our program on the Raspberry Pi. So let's start with creating a virtual environment for our project, and let's activate it. And now let's install important dependencies. Pip install langhain for managing our LLMs. Langhain is installed, and now we can run our Mars rover script. Let's see what happened. We need to wait a little bit for model response. Well, basically, Raspberry Pi is not very fast here, even if we have Raspberry Pi with 8 gigabytes of RAM. It's left about 8 minutes, and finally we have our result here. So basically, LLM at Raspberry Pi is not the best solution when you need real-time or near real-time decision making, but if we have Mars rover that has no access for internet but has a time to think, it will be a good solution. So here we have our JSON returned from our LLM. Based on sensor data, the best direction is go left, as left camera has detected a crater. This could potentially lead to interesting discoveries and further exploration opportunities. The front camera also detects rocks, but it's not as significant as crater detection from the left camera. Interesting reasoning. Basically, I thought he decided clear direction to go discover, but well, maybe crater is also good opportunity. I think it should be better described in prompt what type of surface is runnable and which type is not. So we have our direction left, and activating move function, we are moving to the left direction. Now let's test another situation. Talk about situation where we have mineral detected at our right camera, and the rest of the cameras we have clear view or rocks or crater. And state will be mineral gathering. Okay, let's go now and let's wait another 8 minutes. Whoa, this time it was only 6 minutes. Getting faster. Based on the sensor data, the mineral is most likely located at the right direction as the right camera has detected it. The front camera indicates clear visibility, which means there are no obstacles in that direction. However, the left camera detects a crater, which could potentially hinder movement and make it difficult to navigate. Therefore, we recommend moving in the right direction. Basically, it was right decision because mineral was in right direction and our rover going to the right. Cool. Let's take a look to another scenario where the real power of LLMs get revealed. In third case, we have mineral detected by front camera, but at that direction we have inaccessible rocks. And it's important we need to define that they are really inaccessible, because other way our rover will go through the rocks. So, basically it will be hard to solve such problem using standard programmistic ways. The LLMs coming to be really useful. Let's see how does Zephir will able to process that data and which decision it will make. Let's see on that. Based on the sensor data, the left camera indicates clear terrain, making it the best direction to move in order to avoid any obstacle and potentially find the rare mineral. The front camera's inaccessible rocks and mineral findings suggests that moving forward might not be as fruitful as at this time. The right camera detection of rocks also supports the decision to move left. Therefore, we recommend moving left direction. At that time, our Mars rover going left, and maybe we'll find some walk around for that inaccessible rocks. And after our mineral is gathered, we need to return to base. Here we have base detected by right camera. What will be the decision of our rover in that situation? For the next 7 minutes we have our beautiful reasoning and decision to go to right direction, the direction of the base. So, as we can see, the local LLMs could be successfully used inside of our robots, especially for the cases where our robots will be somewhere outside of internet connection. Zephir LLM was a good example how to do it, but in my opinion, that concrete LLM is not enough to do a really responsible task. Still making a lot of errors according to my experiments, but I hope in near future we'll have a better LLMs that will be able to have less errors, and also hopefully we having all the time better single board computers that will allow us to run on them the bigger LLMs. Thank you for your attention, and let me know in the commentaries what do you think about that application. Do you have any ideas for LLMs applications for your robots? See you!